Hello everyone. So today we'll continue our discussion on liquid-liquid extraction. In previous lecture we discussed about the introduction, about equilibrium and equilateral triangle curve, how to read that curve. And today we'll continue that topic with one of the derivation with some equations and method, how to solve particular examples. So our topic is that stage-wise operation. What is happening in this liquid-liquid extraction? Basically we know that we are having the mixture of feed plus solvent, and at the end of operation we are getting raffinate phase plus extract phase. So that is the basic principle of this liquid liquid extraction, which is shown over here. As you can see that we are having feed, we are having solvent, so at the end of the operation it is raffinate and extract phase we are getting. So let's do the overall material balance, which is based on the flow rate only. So this is feed flow rate plus solvent flow rate. At the end of the operation we are getting raffinate flow rate and extract flow rate. So this is overall material balance, and we know that based on that mixture rule that F plus S, which is equal to M, which is equal to R plus E, that we already discussed that what is mixture rule and or lever arm rule, that F plus S which is equal to M, which means that when we will add our feed and solvent, so we will have some mixture. So in that mixture we would be having some of the composition of solute. So this is the basic principle of this mixture rule. Okay, so now if we'll specially talk about the solute thing, so we'll do the solute balance in this one stage. Okay, so it will be similar to this F plus F equal to M, but here we have to add the weight fraction of the solute. So it is F into XF, which is weight fraction of solute in feed, plus S into YS. That means whatever the solvent we are adding, whether is there any amount of solute available in the solvent or not, which is YS. So basically we are taking it 0 or it is negligible, like 2%, so it will be 0.02 or something, which is equal to M when mixture will happen, and what will be the composition of solute in that mixture. So that is weight fraction of solute, which is XM in the mixture. So based on that, these all parameters are known to us, like feed, what is the composition in the feed, what is the composition in the solute, and the unknown parameter will be M and XM. So how to find out this M and XM and what is the application of that I'll tell you later. So based on this simple equation, if we'll take this XM as subject, so it will be Fxf plus Sys divided by M, and N which can be replaced with F plus S. So all these RHS parameters are known parameter. So based on that we can find out this composition of solute in the mixture when we'll add these two things. Okay, so now the thing is that what is the application of this XM and M point. Here you can see that F plus S equal to M, but we can take this M reference for this R plus E. If we are aware about this R point, and basically we know that what is M point, so we can directly find this E. So that is the application of that. And another application is that how to find that we can use in this equilateral triangle or right angle triangle. And I'll tell you that this right angle triangle method is quite easy compared to this equilateral, because here we have to follow all triangle rules. Okay, but here basically what we are doing, that is y versus x diagram we are taking, and based on that we are plotting this binodal curve. Okay, so that is the application of M point. Now here just see that I'll explain you what is happening in this thing, and I'll explain that in this right triangle. So this is, yeah, so this y-axis and this is x-axis. So on the y-axis we will take weight fraction of solute, and on the x-axis we'll take weight fraction of solvent. So basically you know that here we don't have any kind of weight fraction of that dilutant liquid. Okay, so our focus will be only on the weight fraction of solute in raffinate and extract, and weight fraction of solvent in raffinate and extract point. So we will take these two data, and based on these two data we will draw this binodal curve, as you can see that. Later on I'll explain that thing in the example, but basically what is happening that I'm telling you. this binodal curve is nothing but LLE data, liquid liquid equilibrium data, and based on that we can plot that curve. Okay, so now I'll explain that how to plot this curve and what will be the next procedure that is based on one of the example. Okay, so let's take that example. Here as you can see that 500 kg of solution, that means we have been given F equal to 500. Okay, and 35 weight percent of acetic acid. Yeah, in this system we are having acetic acid and water, and we are using isopropyl ether which is in the pure form. So basically our feed mixture is water plus acetic acid, our diluent which is water, and our focus will be on this solute which is our acetic acid, and for that we are using isopropyl ether which is in the pure form. Okay, so we can say that Ys, that is amount of solute in solvent, which is 0. Okay, because we know that equation that Fxf plus Sys which is equal to Rx plus Ey. So this Ys which is equal to 0, so it would be good for us to calculate the Xm value. Okay, now let's move forward with this question. And we have been given the equilibrium data. Equilibrium is nothing but LLE data. Okay, so here one data which is given water rich phase, which is we know that raffinate phase, and one data which is ether rich phase, which is our extract data. Okay, and this is raffinate. So we are having two different phase data, and as I just told you that in the right angle triangle method or in the equilibrium triangle method, the importance of this solute and solvent is there. Here again solute and solvent is there. We don't involve the data of this dilute and liquid in any of the example. Okay, so again I'll tell you that solute and solvent data are mandatory for the next calculation. Okay, so now similar data that I have put down in this one of the table. So raffinate phase and this is extract phase. So this is the data of solvent and this is solvent and solute. So I just told you that in the right angle curve, we are having on the y-axis which is weight fraction of solute, and over here it is weight fraction of solvent. Okay, so now we are having all the data in raffinate phase, data in extract phase. So similarly I have taken all this data in a single column. Okay, so it would be easy for us to plot this particular graph. Okay, so now what I have done, I have taken this thing that IPA and A. So I'll show you that how to plot the graph. Now I'll select this data. Okay, and I'll plot graph. As you can see that, okay, I have already plot this graph, but how to plot that is what I am showing to you. So this is the graph that I have come up with, as you can see over here. So I told you that this is right angle method. So now we have got this binodal curve, so I'll draw this curve. Right, so this is binodal curve, and in the previous lecture we again discussed that with binodal curve we must have the distribution curve, and this distribution curve, distribution of only solute, that is in raffinate as well as an extract phase. So on the y-axis we are having definitely extract, and on the x-axis we are having raffinate data. So as you can see over here, again I have make this table that acetic acid in raffinate phase and acetic acid in extract phase, and I have plot that graph. And I again told you that we have to take the same units. Okay, so here I have taken 0.125, 0.25. Okay, so this should be same. On the y-axis it would be okay, but on the x-axis it would be okay, but on the y-axis you have to take similar scale, right? And I'll prefer that on the x-axis again you have to take similar, so it would be easy for you. So now this is how we are getting this particular curve with the help of this LLE data, right? So now let us move forward with our question. So this is our question. So now what is the next step? So we'll go step by step. This is a similar graph that I have taken from that sheet. I'll draw binodal curve, and here we have to draw that diagonal. It is 0.25, 0.25, 0.5, 0.5. Okay, it's approximately diagonal. Okay, and here you can see that our this distribution curve which is below the diagonal. Okay, and this is our solubility curve. Now what is the first step? That we are having feed and solvent composition available with us. So what we'll do, we will join this line of this feed and solvent, but it's weight fraction line. Okay, so ys which is equal to 0 and xf which is equal to 0.35 that we have been given in the question. So here from 0 I'll join 0.35 line. So let us assume it is somewhere around here. Okay, so this is the first step that we have to do, that this is S point and this is F point. This is very important. This is first step to find out the amount of raffinate and extract for the single stage. Now second, I told you that then we have to find out F plus S equal to mixture, that what's the amount of solute in mixture which is our xm, and we know that xm which is equal to fxf plus sys divided by f plus f. So based on that calculation we are getting xm which is 0.175. okay, so it is 0.175 which is amount of solute, and we know that solute which is available on this y-axis, so we have to find this 0.175 somewhere over here. Okay, so let us assume that it is over here. This is the point, and we again know that M point will be only on this FS line. Okay, so yes, let us assume that this is our M point. So this is our second step, that based on this XM calculation we have to point down this M point on this FS line. Now I told you that the importance of this M point, that to find out raffinate and extract. So we know that R plus E again which is equal to M. So in this procedure what we have to do, we have to assume one of the point of raffinate in this curve, and based on that we have to come up with this E. So just see here, I'll here assume, let's assume that my R point is somewhere around here. This is what I am assuming, which is something 0.3. okay, so now we are having this R point. So based on this equation we can explain that R and M point will extend to the solubility curve up to E point. Okay, so I'll again join this line RM. So if I'll expand this particular thing, so it will be somewhere around here. So I can say that this is my extract point. So the value of R which I assume, which is right or wrong, that I have to check. Okay, so how to check that? So what we have to do, just extend this line up to diagonal. Okay, then we'll go vertical up to this curve. Okay, then again we'll come back to this curve. Okay, so as you can see that this is my assumption that it is R this point, and based on the assumption I have come up with this point, but actually it should be somewhere around here. So this my assumption is wrong. Okay, So this is how we have to do trial and error method. We have to assume this R data such a way that by this method we will come up with the same point which is passing through this uh, M line. Okay, so this is what I have done in this example, that it is somewhere around 0.28 or something. From that point I have initiated and I have come up with this line. Okay, and the exact or similar assumptions that I have got. So this is the final raffinate and extract data. So from this point what we are getting, this is what it is, amount in the raffinate, and this is amount in extract. This is raffinate. Okay, so in one stage if we'll perform the liquid extraction, so the amount that we have got, that I have written somewhere around here, of acetic acid, it is 0.257, as you can see that something around 0.257, and in the extract phase we have got 0.115. Okay, which is this data 0.115. Okay, so this is how we can come to know that what will be the final composition of solute in raffinate phase as well as in the extract phase. Now based on this composition we can directly find that what will be R value, because all these parameter are known to us. Okay, so that's it. This is the procedure, that how to find out R and E, or the amount of solute in raffinate and extract with the single stage extraction. Thank you so much.